Howdy everyone, and welcome to this video lecture series on general chemistry. The goal of this series is to provide shorter, easy to digest videos that will cover many of the major topics that you will encounter in a general chemistry course. It's not going to be a replacement for showing up to class. It's going to be a supplement that you can go back, maybe get something a little bit easier. Maybe you watch these ahead of time, come up with questions, and then as you go through the in-person lecture, you can ask them or get clarification when that material comes up. But think of this as a second way to learn the information, to help it sink in a little bit better, and hopefully improve your outcomes in this course. All right, so we're going to start with Chapter 1. I'm using the Brown, LeMay, and Burston Chemistry, the Central Science book. But many other books, if you ever wind up with one, they will cover the same material in a very similar order. Most general chemistry textbooks kind of go in the same way. I will jump around a little bit, but we'll just get to it. All right, so we're starting here with Chapter 1, Part 1 on matter. And so the idea being, what is chemistry? What are we going to be looking at in this course? And so first off, we always say here that chemistry is the study of matter and its interactions. The idea being this is, what if we take these two substances and put them together? Does something happen? Maybe we have to add heat. Maybe we have to put it in a microwave, an oven, shine a light on it. Sometimes it's just one type of matter, and if we heat it up, something will happen. Chemistry is the study of all of that, whether it's making new compounds, breaking a compound down, mixing things together, or just taking one compound and changing it, like boiling it. That's all chemistry. And so that's what we're looking at. And so we say, well, what is matter then? Well, it seems kind of general. Well, it is. Matter is a good chunk of the universe. Matter is anything with mass that occupies space. Some will refer to it as it has mass and volume. But if it has mass, if it has takes up space, that's matter. So everything, the air, this pencil I've got in my hand, just anything around you, the paper you're writing on, it's all matter. Okay? And so chemistry is a very broad field. There's just so much to study, and that's why when you get higher up, you get to different divisions of chemistry. We've got organic, inorganic, biochem, analytical. Just, you can pair it in with stuff out in space, astrochemistry. Just what's all around us? Well, it's all stuff to be studied for chemistry. And so we're going to go through and say, okay, well, if we got to start with matter here, we've got to be able to start organizing a little bit. And that's what we're going to do next. We're going to start classifying matter. So we can first do that by saying we can have classification by phase or by state. And so many people remember from, say, middle school science, the states of matter. We've got solids, we've got liquids, and we've got gases. And so solids, they have the same shape, they keep the same volume, the particles aren't moving. Liquids, well, the particles start moving around, but they stay in contact with each other, so while the shape can change, the volume does not. And then gases, well, those particles are far apart from each other, they're flying around, so they can change shape, change volume, just go everywhere. And so that's one way of classifying matter. It's a pretty easy way, because it doesn't matter what the matter is. Just, well, is it solid, liquid, or gas? Base it on those properties. But there's another way of classifying where we can do classification by composition. And the idea here is we can say what is the matter made of? Whether it's solid, liquid, or gas, what's it made of? That's what we're going to go for. And so there's two main categories. We're going to start with the first one, where we have pure substances. And a pure substance has a couple properties. It is made of one, and we'll just say thing, right? There could be more than one thing in there, but it's one thing, that everything in that pure substance is the same. It's identical. Right? It cannot be physically separated. And so we'll talk about the physical methods of separation in a little bit here. But the idea is, you can't filter a pure substance apart. You can't filter, or you can't use some type of grating or like a colander or anything and say, oh, well, it was pure and now I've split it up into something simpler. No, it's always going to be pure. It's always going to be the same thing by physical means. And so we say, okay, well, great. What does that mean? Well, we've got two types of pure substances. The number one type is an element. An element is made of only one type of atom. And of course, atoms are our building blocks. They are the smallest piece of matter that we deal with in chemistry. Yes, you can get smaller, and well, we will when we go subatomic there, but it's the smallest part that has chemical properties. So elements are only made of one type of atom. They cannot be chemically simplified or chemically separated. So if you have an element, well, that's what you have. No matter what you do to it, you can't make it any simpler than it already is, at least not by chemical means. All right? And I think we'll leave it there just for a basic definition that, okay, yeah, it's one type. The second type of pure substance, so this is still a pure substance. We call it a compound. And that's when it's made of more than one atom. But the key here, it's in a fixed ratio. And that fixed ratio often takes the form of a formula, which we'll talk more about in Chapter 2. But just as an example, most people know water is H2O. This idea of two hydrogen atoms and one oxygen atom all connected together to make water. That's a compound. So every water molecule is H2O. They're all the same. That's why it's still considered pure. Right? These can be chemically simplified. So if I take that water and I put it in the correct apparatus, we call it a Hoffman apparatus usually, but if I electrocute the water the right way, I will produce hydrogen gas and I will produce oxygen gas. I can separate the H2O into the hydrogen and the oxygen. If I have an element, I can't do that. So that's the main difference, that compounds, more than one thing, but they've got that ratio. Elements, just one thing, just the hydrogen, just the oxygen, just the carbon. The cheat is if it's on the periodic table of the elements, it's an element. All right, well, what about not pure substances then? If we had pure substance, well then we've got impure, but we don't call them impure, we call them mixtures. So that is when you, excuse me, when you have more than one substance. The key things with mixtures is that they can have a variable composition. What that means is that even though you have more than one thing, it might not always be the same amounts of each thing. So the example I always use, I love sweet tea. not every restaurant puts nearly enough sugar in it, right? Some people, when they like tea, oh, I'll take an unsweetened tea, and they just add 1 packet of sugar. Some people add 2 packets. Some people add 3. I like to add a whole cup. Either way, we can have different amounts of sugar in that tea, but as long as it all mixes up together, it's still a mixture. It just has a variable composition. It can have different amounts of each thing. All right? So we have 2 types of mixtures. The first type is called homogeneous, and that's where everything in the mixture, let's say the way we like to say it, is uniform. It's a uniform mixture, meaning it all looks the same, right? So again, the sweet tea, if all the sugar dissolves and all those tea compounds are dissolved in the water and the caffeine's dissolved in the water, everything's mixed up, well, every bit of tea in the cup is going to look like every other bit of tea. It all looks the same. It's homogeneous. Right? The other type of mixture is heterogeneous. This is when it's non-uniform, meaning you can see the different parts. And so a chocolate chip cookie, lots of ingredients went in, they all got mixed up, but when you look at it, you can see the chocolate chips, you can see the cookies. Fruit salad, yeah, it's all mixed up, all the different fruit, but oh, that's a pineapple, and that's an apple, and that's a grape, and that's a strawberry. You can tell the different parts. So if it all looks the same, homogeneous. If you can tell the different parts apart, heterogeneous. Now there are some other ones where the book might mention things like colloids and suspensions. They're kind of in between, where it's like you might, suspensions where you have a solid particle that's not dissolved. Okay, so that's kind of heterogeneous. They're not really together. But they float around so evenly that they're pretty evenly mixed up. So it looks more uniform. So it's kind of we're not going to worry too much about those. Homogeneous and heterogeneous are the 2 that I would focus on. All right. So when we then move on there, say, okay, well, what about that physical separation? We said pure substances can't be physically separated. Well, that implies that mixtures can be, and they can. I probably should have put that in. Let's insert the notes. Can be physically separated, and that line has been there this entire time. All right. Well, what does that mean? What are our physical methods of separation? Well, we've got a couple. The number 1 that we use in lab a lot is filtration. And filtration is typically used when you have a liquid and a solid. So we're using physical differences of the properties to say, oh, we've got something that's a liquid, something that's solid, that's a difference in physical state. We can use that to separate. So how does that work? Well, it's just we have usually a filter paper. We'll just do that. We'll make this a funnel. And so as we pour our mixture in, our solid gets stuck on the paper, and then we'll just have some water dripping. The liquid comes through, and it depends on the experiment. Sometimes we want to keep the solid, sometimes we want to keep the liquid, sometimes we want to keep both. But filtration is a great method for how do we separate one from the other. All right. Our next common filtering technique is called distillation. And I would encourage you to find the figure for this in the textbook to kind of see the setup. I'm not going to try to draw the whole thing. It's figure 1.12 in my textbook, but it's going to be in that separation section of whichever textbook you have. The idea here, this is where we can separate a liquid and another liquid from each other. And the idea is it separates based on boiling points. And so you have 2 liquids maybe one of them boils at 70 Celsius, the other one boils at 120. Well, if you heat up your container to about 75, 80 Celsius, well, then that lower boiling point one will heat up, it'll turn into a gas, but the one that boils at 120, no, it's going to stay a liquid. And then the idea of the setup, which I guess I am going to try to draw here, we have like usually a flask, and then there's a hose that goes up, and then we have a condenser, and then that drips into another beaker. So we have our mixture here. The idea is, and I'll draw this, usually a lot of textbooks will say, okay, yeah, we've got a green mixture, but when we heat this up, say it's like blue and yellow mixed together, the yellow gets left behind, and the blue stuff floats up, turns into a liquid here, and then we can get the blue liquid to collect over there. And so there's other stuff that goes along with it, but the idea is we have this difference in a physical property, the boiling point, and we can exploit that. If you go on to take organic chemistry, distillation will become very important because so many experiments in organic chemistry rely on distillation to separate different liquids or separate a product out from the mixture. All right. Another type of separation method is called chromatography. Chromatography. This separates based on what we call intermolecular forces. The idea is if you have a molecule, if you have some substance, it will interact with other substances. And sometimes it interacts only a really little bit, sometimes it interacts a whole lot. And so the idea is when we have, whether it's a piece of paper, a gel column, a thin layer, liquid, there's many different chromatography techniques, but some things will not stick at all and they'll just travel through quickly. Some things will stick really well and they'll move more slowly. And so based on time, you can say, oh, this stuff will come out first, then this stuff, then this stuff. So there is a picture of chromatography, figure 113 in the book. But that's for a column chromatography. But I'm not going to worry about that too much because that's chapter 11 for intermolecular forces, and that's in Chem 106. So we'll come back to that if you go on to 106 to talk about that. There is one other technique that the book does not mention, decanting. And this is just careful pouring. And so this is often used to also separate a liquid and a solid. Sometimes you'll get it where the solid, like we talked about suspensions, it's floating around, it's all that. That's where you need to use filtration because, that's the only way to separate them. But if you have a solid that sticks to itself really well and sinks to the bottom of your beaker really well, then sometimes all you have to do is let it settle to the bottom and then just carefully tilt your beaker and pour the liquid off on top. And then you can have, oh, here's my liquid with none of the solid in it, and then here's my solid with maybe just a little liquid left, and I can get rid of that by some other means. But decanting, very quick, very easy. It's actually commonly used just because of, why do something that requires a lot more setup if you can get the job done in a fraction of the time and a fraction of the effort. All right, so there's some separation techniques. But we said they're all based on physical properties. Well, let's talk about that a little bit more. What is a physical property? And then what is a physical change? What's a chemical property? What's a chemical change? So the key thing is that a property is a characteristic of a material that can be observed. Okay, so it's like, oh, well, what's something that we could characterize? So if I held up, say this pen, if I said characterize it, you might say, okay, it's longer than it is wider. It's gray. It's got a little bit of shine to it. Well, those are all properties. So that's what we're looking at when we say we observed it. That's a property. So there's two types of properties. The first type is a physical property. That's where it is observed without altering the chemical composition. Okay. And so what we just did with this pen, those were all physical because I still have the pen. I didn't do anything to it. All right, so things like color, odor, mass, volume, the more complicated ones, melting point, and likewise the boiling point. These are all physical properties, and there's many more because we can measure it without changing it. And so the melting point and boiling point, that's where people sometimes get confused. So I like to think of just keep it simple with water. If we are saying, okay, we're taking liquid water and turning into ice, because right, melting point, freezing point, same thing, same temperature. When we turn water into ice, is it still water? Is it still H2O? Yes, it is. Okay, so we could find that melting point without changing the chemical, without changing water. Well, that's why it's a physical property. Same thing for boiling. When water boils and turns into steam, it's still water, it's still H2O, it's just a gas now. And so we haven't changed the chemical composition, so finding and observing that boiling point, that's still just a physical property. All right. The other type is a chemical property. And so it's kind of the opposite definition. It is only observed by altering the chemical. And so common example is paper burning. We all know that paper will burn. But how do we see it? Well, the only way to see it is to actually burn the paper, and then, well, we don't have paper anymore. It's going through a reaction. It's turned into carbon dioxide and water and some ashes on the table. And so that's a chemical property. Even if we know it will happen, we can't see it happen unless we actually do it. So chemical properties, there's fewer of them. It's all things related to reactivity. Right? So as one type of reactivity, flammability. Right? Even if we know something will burn, we can't observe it until we actually burn it and lose the chemical to make it something else. Right? Well, along those lines, we can also have physical and chemical changes. All right, so let's talk about that. So when we have changes, this is when we have an alteration of properties. All right. So we started with some set of properties, maybe color, odor, state of matter, whatever, and at the end we have a different set. All right. So physical, again, we have physical and chemical. A physical change stays the same material. Right? That we change it somehow, but it's still the same chemicals. And so some examples of that. Things like melting and boiling. Right? We said again with our water example. It's still water. It's still H2O even when it freezes, when it melts, when it boils, condenses. It's still water. That's a physical change. It's just going from solid, liquid to gas and vice versa. Other examples of physical changes are mixing and separating. Right? So if I take, say, again, going back to our sweet tea example, I've got some iced tea, I've got some sugar, I mix them together, I still have iced tea and sugar, just now they're in the same glass, they've been mixed. If for some reason I want to separate them, well, I'm probably going to have to do a mixture of separation techniques, the things, maybe some distillation to get the water away, and then I can try to separate the sugar out from all stuff. It could be done. It'd be really odd, but it could be done. That's also, again, I'd still have water, I'd still have sugar, I'd still have the tea. That's physical changes. All right? So if you don't change what the actual chemicals are, it's a physical change. But then the other type, a chemical change, here you do get new chemicals as a result. Different chemicals than what you started with. And so this, a chemical change, has a special name. We call it a chemical reaction. Right? So when later in the course, when we get to balanced reactions in chapter 3, all that stuff about, if we start with this and end with that, every single reaction is a chemical reaction. That's what or a chemical change. That's what we're going for. So chemical changes are the big thing. All right, and I think we're going to stop there for this first segment. Again, we're just looking for highlights. But again, go through these videos, use them as a resource to say, what do I need to brush up on? Maybe just hearing something again in a slightly different way. Maybe that helps you out. But stay tuned, look through the playlist for more videos on what you need, and have a wonderful day.